All right, guys, let's knock out our 5.2 notes. I did shorten down the notes just a little bit for what's available on Schoology versus here, just so this video is not wicked long. It's nice and short and concise for what we need it to do. I am going to go ahead and just point out a couple things. Sorry, my eye itches. In any case, yeah, so let's just get rolling. So we've already looked at gases. We looked at pressure. We were able to convert pressure in a couple different ways, and that the pressure of a gas has to deal with how much outside force is pushing on that gas compared to the inside force pushing out. Think of a balloon, right? A balloon is going to have equal pressure inside as it does outside. Well, lo and behold, a couple scientists, first one being here, Boyle. Boyle came up with the idea of testing gases and their compressibility. I mean, how much could you squeeze them? And he found out pressure and volume have a relationship. So if I take a balloon, blow it up, and I wanted to increase the pressure inside the balloon, what would I do? I would squeeze the balloon. I'd make that volume smaller. And so Robert Boyle here kind of discovered that there's a relationship between pressure and volume of a gas. And that relationship is what's considered an indirect relationship. So let's add a little bit to the slide we got here. And there we go. I don't want to get too far out of picture, out of frame. And so he found out that it's an indirect relationship. Let me get all this lined up nice and clean. So there's also indirect, are also called inverse. So indirect, or also called inverse relationship. And that means as pressure goes up on a gas, volume has to go down. Or if pressure goes down, volume has to go up. They're opposite of each other. So if you look at my thumbs, they're indirect or inverse of each other. We could look at this equation right here. I don't care too much for it. We're just going to look at the other version of his equation, which is P1V1 equals P2V2, meaning the pressure and volume of a gas. We're able to predict what its pressure and volume would be if you keep everything else constant. What are some other things that could affect a gas? That could be temperature. So it's at a specific temperature, and number of moles. Or you could also say grams. That would work as well. So if I have a balloon and I tie it off, we're going to keep temperature constant. We're also going to keep how much gas is in there constant. What we're not going to change is anything else. We were looking at just pressure and volume. Here's what we can do with it, though. We can use this formula to predict the pressure and volume of a gas. With this, we kind of came up with the idea of an ideal gas. So ideal gas is any gas we're going to deal with are going to follow the same mathematical formulas. We're not too concerned about changes or differences, but we're just going to call every gas in this class an ideal gas. So let's look at this question right here, and then kind of go from here. Pause the video, give it a read, and then identify what would be the important information out of this question. Okay, give it a chance, give it a read. I'm drinking coffee at 10:15 at night because we got to get rolling. We got stuff to do. But we've got some pressure values in pascals. We also have our liters or volumes. So what are we given? We're given pressure 1 equals 5.6 times 10 to the third pascals. And pressure 2 is 1.5 times 10 to the fourth pascals. Volume 1, our initial volume, is 1.53 liters. Not too bad. So we're just going to follow that mathematical formula we got for Boyle's law. P1V1 equals P2V2. Before I do that, let's ask the question, would I expect the volume to increase or decrease here? Well, our pressure went from a number to a bigger number. So pressure increases, which means volume has to decrease. If we did our math correctly, our volume should be smaller. So let's go ahead and plug in those numbers. We've got 5.6 times 10 to the 3 times volume 1. Actually, you know what? Actually, let's erase this. I want to write this a little bit different way. I don't want to be rewriting these numbers out a lot. So let's go ahead and get V2 by itself here. And how would I do that? Well, I would divide both sides by P2. So I get as V2 equals P1, pressure 1, volume 1, all over pressure 2. This allows me to save time of rewriting numbers. We've already solved our equation to the variable we're looking for, and we're looking for V2. So V2 is already by itself. So we're able to now just plug and chug our numbers in and go from here. So P1 is 5.6 times 10 to the third times 1.53, all divided by 1.5 times 10 to the fourth. I'm going to go ahead and pull up my calculator, and you can pull up yours too and learn how to use this. I'm going to type this in a graphing calculator, so if you want to use the ones in my class, you're welcome to use the ones in my class. But we're going to type in this number here. I don't care which calculator you use, just make sure that the numbers you get are the ones I get. I want you to be comfortable with the calculator you're using. I'd hate for you to get a question wrong because you're using a calculator you're not familiar with. So 5.6 times 10, so I'm going to do second EE. This E right here means times 10. Times 10 to the power of what? 3. Times 1.53 divided by 1.5 second EE to the 4. And we get the answer of 0.5712. So our final answer here is 0.5712, and that would be in liters. Cool, not too bad. Here's what I want you to do now. I want you to pause in this video and try this one by yourself. I am going to give you one hint though. All right, earlier our units were in the same unit. This time they're not, okay? So we need to convert both of those into the same unit. They could both be liters, they could both be milliliters, doesn't matter for this instance, but we need to convert those before we plug and chug in our calculations. Pause the video, give it a shot, and then I'm going to go ahead and get started because you pause the video and do this problem on your own. P1 equals 5.2 atmospheres. V1 is 400 milliliters. I'm going to convert that into liters. So that's going to be 0.4 liters divided by 1,000. V2 equals 2.14 liters. And we're looking for pressure too. So before I do any math, let's ask the question. What happened to my volume? My volume went from a small number to a bigger number, so volume increased. What should pressure do then? Well, pressure should decrease because if volume goes up, pressure has to go down because it's an indirect relationship. So let's do P1 V1 equals P2 V2. I'm going to go ahead and get P2 by itself. So P2 equals P1 V1 all over V2. And then let's plug and chug our numbers from here. We've got 0.4. Well, let's do correct order here. Let's do 5.2 times 0.4 divided by 2.14. And what's that number going to be? Let's go to my calculator. Let's try that. So it'll be 5.2 times 0.4 divided by 2.14. And we get 0.9712. I think it was 12. Let's double check that. Let's do view, always in front. There we go. 9719. Let's 0.972 atmospheres, because that's in pressure. Alrighty. There we go, folks. That's all you do with Boyle's Law. Let's go ahead and keep moving on. We're going to now unpack Charles's Law. So Boyle's look at pressure and volume. Charles's Law looks at volume and temperature. So what we did earlier on that last one, where we didn't really use this equation, I don't like it too much. Instead, we're going to use V1 over T1 equals V2 over T2. Okay? Before we can unpack this too much, there's something we have to notice is that temperature is always going to be in Kelvin. So let's look at, what was that? I don't know what that was. Let me check something out real quick. Oh, YouTube's running in the background, but the audio's off. Alrighty. Any case, let's keep going. Alright. We have temperature. Temperature's measured in Celsius or Kelvin. Well, there's 3 scales to measure temperature: Fahrenheit, Celsius, and Kelvin. We're only concerned about Kelvin. So how do you convert from Celsius to Kelvin? That would be K minus 273. Okay? That's it. So a couple things. We will always want to be in Kelvin. Notice it's not degrees Kelvin, it's just Kelvin. All right. When we're using our calculations here. V1 over T1 equals V2 over T2. There's our formula. There's our calculations. But what kind of relationship is this? Well, this is a direct relationship. Meaning as volume increases, temperature would also increase. Or volume decreases, temperature also decreases. That's how a hot air balloon works. Keyword, hot air balloon. The hotter it is, the more the balloon's filled up. All right. If I were to take a balloon and throw it out outside in the middle of winter right now, we'd expect that balloon to shrink. That's because the temperature goes down. So Charles's Law looked at the volume of a gas with its temperature. But the one thing we always have to be worried about is temperature in Kelvin. And they always needs to be in Kelvin. So what I want you to do is, using those 2 formulas we have, let's now they'll solve this problem. So go ahead and pause in the video, try it out. Got to convert to Kelvin, and then try it out on your own. Okay, so we have, what do we got? We got T1 equals 15 degrees Celsius. To convert to Kelvin, you would do 15 plus 273. So that would be 288. 288 Kelvin. Temperature 2 would be 38 degrees Celsius. So that'd be 38 plus 273. That'd be 311 Kelvin. And pressure 1. Well, pressure doesn't change. Pressure 1 is pressure 2. Doesn't change. Doesn't help me there. But we do have is volume. Volume is 2.58 liters. Volume 2, we do not know. So let's use V1 over T1 equals V2 over T2. We're looking for V2, so I'm going to go ahead and get V2 by itself here. I'm going to multiply both sides by T2. And so what I get is V2, because these cancel out, let's do that in a different color so we can see it nice and clean. T2s cancel out over here. And so I'm left with V2 equals V1 T2 all over T1. Plug and chug, let's go. 2.58. T2 is 311 Kelvin. Remember, we got to use Kelvin. All over T1, which is 288. Looks good to me. Let's bring the calculator up so we can see this in action. So that'd be 2.58 times 311 divided by 288. And we get 2.78. Make sure I'm following along. I'm not missing my other notes here. I feel like I'm missing something from earlier. Nope, we're looking okay. So I'm going to do 2.78. So we'll do 79, and that's in volume, so that would be liters. There we go. Looking good. So we just did a little bit of Boyle, a little bit of Charles's law. Now we're going to move over to Avogadro's law. Okay. Which is going to be the same thing. We're going to look at a gas. Other things are going to be constant. So temperature and pressure are constant. The only thing that changes is the amount of moles or in the volume of a gas. So if I take a balloon and I were to I got a deflated balloon and I were to pump more air into it, you'd expect the volume of the balloon to increase. So as we increase the number of moles, you increase volume. Well, what kind of relationship is that? Well, that would be a direct relationship again. So as we increase the number of moles, which is denoted by the letter M, volume increases. Or if we decrease the number of moles, volume decreases. It's a direct relationship. And if we were to graph that, like Vn, it'd be direct relationship. We're not worried about this, the way how this is written, because we're just going to do V1 over N1 equals V2 over N2. We're going to use this equation right here to help us solve this problem. You might notice some patterns. Pattern recognition is great. Let's just use that when we're looking at these problems. Okay. What do we got here? Let's pause the video, read the question, write down what information is given, and then let's try to solve this together. So I got V1 equals 12.2 liters. We have N1, which is 0.5 moles of oxygen gas, so O2. Pressure and temperature, well, pressure and temperature are the same, so P1 equals P2, doesn't help me anywhere. T1 equals T2, doesn't help me anywhere. And we're looking for the new volume. Well, how do I do my number of moles? We got to do a mole-to-mole conversion. Before we can do a mole-to-mole conversion, we need to have a chemical reaction. The oxygen gas, O2, was converted into O3, ozone. Let's go ahead and balance that. So if we were to balance that chemical reaction, that'd be a 3 and a 2. And how many moles of oxygen did I start off with? Well, 0.5 moles of O2. Remember, whatever unit's on top left immediately goes in the bottom right. And we're going to moles of O3. What number is next to O2? Well, that's a 3. Next to O3 is a 2. Let me draw those in red and maybe put an arrow in there just so you know where those numbers came from. So 0.5 times 2 divided by 3, well, that's 0.33 moles of O3. Hey, look at that. I've now got volume. I have my two numbers of moles. And we can now find out N2. So N2 is 0.33 moles of O2. I think we have enough to solve this problem. Let's do it. Let's check it out. V1 N1 equals V2 N2. Let's get volume by itself. So I'm going to multiply both sides by N2. N2's cancel out. Ding, ding. I'm left with V2 equals N2 V1 all over N1. It's just plug and chug from there, baby. So that's going to be 0.33. V1 is 12.2. And N1 is 0.5. Bring my calculator back in. Let's try this number out. So that's going to be 0.33 times 12.2 divided by 0.5. And I get a final answer of 8.052 liters. Cool. Alrighty, folks. I think we're cooking with grease. We got one last example to do. And I think either we're going to be done or we're going to be really, really, really close. We'll see. What I want you to do, try this out for me. I want you to pause this video. Try out this problem. Okay? Yeah, pause the video, try this problem out. And then we've covered the notes. We'll do a couple of practice problems here at the end, just so we can try some out what we've learned. But other than that, we're wrapping it up, folks. Okay, 12.1 grams of argon. Ooh, I need to convert that to moles. So before I even do anything else, 27.1 grams of argon. We got to convert that to moles because we always need to deal in moles. Well, what's the molar mass of argon? So looking at the periodic table, that's going to be 39.9. You could use 40, sure. Equals 1 mole. And that's going to get me 0.68 moles of argon. Okay, so I already know N1 equals 0.68 moles of argon. The volume for that argon is 4.21. What volume will 1.29 moles of neon be at the same temperature and pressure? So we don't know V2. Let's do it out. V1 over N1 equals V2 over N2. Get V2 by itself. Multiply both sides by N2. So I get is V2. Let's do some red here so we can see that those cancel out. So V2 equals V1, N2, all over N1. So we got 4.21 times, well, this should be N2. 4.21 times 0.68 all over 1. I tried to fix my boo-boo and I made more boo-boos. Let's fix that. V1, which is 4.21. N2, which is 1.29. All over N1, which is 0.68. There we go. There we go. There we go. There we go. Cooking with grease, folks. 4.21 times 1.29 divided by 0.68 gets us a whopping 7.9. Is that right? 0.68. 4.21. Why is my answer different than what I had earlier? I think that's because I used 40. We'll go with it. We'll call it rounding error. 7.98 liters. So 99, let's do 99 liters. There we go. We'll call that one done. There's some rounding error in there, but I'm not too concerned about it. Alrighty, guys. That's going to be it as far as notes go. Let's do a couple of example problems together, or at least some practice multiple choice questions. Okay? Pause the video, try it out, see what you get. Okay? A balloon contains a certain mass of neon gas, temperature is held constant, and there is some argon gas added to the balloon. What's going to happen to the balloon? What I would accept, right, would be a balloon doubles in volume. I would understand why you'd want to say that. However, the balloon would only double in volume if you added the same gas to it. Neon and argon have different densities, different masses. So the balloon is not going to double in volume. I can see how you'd want to think that, though. What I will say, though, is the balloon will not stay the same size. And they're definitely going to expand. Is it going to expand by more than 2 times or less than 2 times? Well, it's going to be less than 2 times. Because you're not going to add argon to it, and it's going to expand more, double. So it'd be less than 2 times the volume. All right. Each of these balloons hold 1 liter of different gases. All of them are at the same temperature. All contain the same number of molecules. What would have to be the same for each balloon? Well, here's the deal. They have the same number of molecules. They're at the same volume. They're at the same temperature. We can assume, since they're all balloons, they're at the same pressure. Well, actually, can we assume the same pressure? We can't assume this. It's not given to us. I know it looks like in the picture it could be, but we can't assume that. What we can know is that they're different. Since they're different substances, their masses are going to be different. So look at density equals mass divided by volume, right? All the volumes are the same. Are their masses the same? If I had a helium balloon and a nitrogen balloon, would they have the same mass? That is not the same. So what we would say is, well, their masses are going to be different. They're going to have different weights to them. If they have different weights, different masses, absolutely. They're going to have different densities. They're also going to have different buoyancies. If I have a balloon of oxygen and a balloon of helium, the helium balloon is going to want to fly up into the atmosphere. The oxygen balloon is going to just piddle on the ground. So we would then, by default, have to say their pressures are the same. I like this question. A cylinder is fitted with a movable piston. We'll call P1 and V1. What is the new pressure in the system if the piston decreases the volume of the cylinder by half? So we got P1, we got V1, P2, V2. If the piston decreases the volume by half, that means volume 1 is 2 times volume 2. Follow me there? So if the piston decreases by half, so if I've got a piston here, and we got a plunger, and that plunger decreases the volume by half. If this is V1, this is V2. That means the volume of 2 is half, or it would take 2 times as much to be the same as volume 1. I can then plug this into here. Watch this. P1 2V2 equals P2 V2. Hey. So what else cancels out? Well, look at this. V2 cancels out. And what are we looking for? What is the new pressure? We're looking for P2. So what I have is P2 is twice the pressure of P1. Does that make sense? Absolutely. If volume goes down, pressure goes up. If volume's cut in half, pressure doubles by 2. I guess doubles by 2 would be that's an oxymoron. It doubles. Cool. Alrighty. That's it, guys, for 5.2 notes. You guys are awesome. Stay awesome, and I will see you in class.